about this section, I quite often find that it takes students a lot of practice. The rules are a little strange, especially when you're dealing with trying to translate radicals, and we're going to do some of that today. But especially when you're trying to translate radicals and you have things like negative exponents and negative exponents that are fractions, and it just looks really bad. So what you have to do is get your rules set in your mind, and these pages that we're going to cover today are going to sort of help you with that. But after the rules are set, then it does take quite a bit of practice to get through this. I want to go over first, let's start here, and let's talk about what a like radical is. A like radical is when whatever's under the radical sign is exactly the same, okay? Need help, or are you okay? You got it? Okay, so what's under the radical sign is exactly the same here. When that happens, now we're assuming that there's no variable outside of the radical sign, because we'll cover that in just a second. But when that happens, then you can just treat it like this was 6x plus 5x, okay? The thing is, they have the same, that coefficient has the same thing that it's being multiplied by. You understand? So then you get to just do whatever this math is in the middle, and you get to add them. So what we really have here is 11 times the square root of x, right? I'm sorry, times the square root of 7. Just like you would have had 11x if you had added terms that had x as the variable, as the unknown, okay? So the square root of 7 doesn't really have to be resolved in these cases. Now let's take a look at these. These do not have the same thing under the radical sign, do they? This one is the cube root of 5x, and this one is the cube root of 40x. Those cannot be subtracted, added, anything like that. But we might be able to do something with this one. Look at your first one. There's nothing I can do about the cube root of 5, is there? There's nothing I can do about the cube root of x. I cannot simplify that any further. So I'm simply going to say that one stays as it is. It is the cube root of 5x. But I'm going to say, what can I do with this 40x? Well, I can look for perfect cubes inside 40, can't I? So I would come over here and go, okay, perfect cubes. If I'm trying to find cubes, I need 3 numbers that are multiplied together that give me 40, don't I? Or give me something. So I'm going to just kind of break it down to primes if I don't see it right away. I see the perfect cube in 40, but if you're not used to cubes, you might not. So you break it down into primes. If it's an even number, you can always start dividing by 2. And 40 divided by 2 is 20. I'll do this one again because it's still not down to primes. And 20 divided by 2 is 10. And 10 divided by 2 is going to be 5. And now I'm done because I can't go any further. But I do see a perfect cube. 2 times 2 times 2 is 8. 8 is a perfect cube. Guys, memorize some of your cubes. I would memorize at least up to 6. You know, 1 cubed, 2 cubed, 3 cubed, 4, all the way up to 6 cubed. It will really help you. Jot them down on an index card, memorize them, okay? Because otherwise you're going to be breaking down everything into primes. And eventually, if you can see the perfect cubes, you don't have to go through this step. You can shorten your process. So if I was writing it and I was trying to do what we did the other day, I'd say the cube root of 2 times 2 times 2 times 5 times x is what that really breaks down into. And I can bring this out from under the radical. The cube root of 2 times 2 times 2 is just one of those 2's, isn't it? However, the 5 and the x, there's nothing I can do about them, and they have to stay. So what do I have finally? Well, I have the cube root of 5x minus, and what happens to this is this 2 that I brought out gets multiplied times the coefficient that's in front of my radical, which is a coefficient of 1, isn't it? So that's 2 times the cube root of whatever it was left, which was only 5x. Now, I have the same radical in both of my terms. I have the same unknown here. I have the same variable, don't I? Cube root of 5x, cube root of 5x. So this one is really one of those. 1 minus 2 is always going to be a negative 1, or we could just say negative the cube root of 5x. Okay? Yes? Oh, sure. I think I have one right here. There you go.
Thank you so much.
Okay, next problem. Let's look and see what happens with this 81x squared. Once again, cube roots. And this one is what's under the radical is 24x squared. Now, I already know that there's no perfect cube inside an x squared. It's not divisible by 3. It's not bigger than a multiple of 3. So I'm stuck with that x squared. But I don't know about the 81. So I'm going to come right over here and I'm going to say break 81 down. Do you know a perfect cube inside 81? Chances are you don't. So what will it divide by? Well, it won't divide by 5, will it? It won't divide by 2. The next number you check is 3. Now, how do I know that it'll divide by 3? Because 8 plus 1 is equal to 9, and 9 is divisible by 3, so the 81 is also divisible by 3. That little trick only works for 3's, okay? So I take 81, and I say divided by 3, and I get 27. Now I keep on going. Well, that won't divide by 2 or 5, but it will divide by 3, so I go divided by 3 again, and I get 9. And by now, you knew that, right? So you could just keep on going. So what is 81? Broken to primes, it's 3 times 3 times 3 times 3. I do have a perfect cube in there. 3 of those 3's will do it. I'm going to have to move over here to write it. So I'm going to say the cube root of 3 times 3 times 3 times 3 times x squared, because there's no reason to break that down. It won't go anywhere. And then I'm going to go ahead and simplify it while I'm thinking about it. I'm going to say this is the perfect cube in there. Take it out. I just need one of them. And this is what's left over. So to simplify the cube root of 81x squared, it's really 3 times the cube root of 3x squared. Can you see that okay? Blow it up a little for you. Does that help? Just remind me, because I'll probably run off the page now that I've got it so big, okay? So that takes care of that one. Let's say this one. Don't forget the operation in the middle we have to keep up with, okay? Minus 5 times, okay, here's another cube root. And I don't know cubes, so I'm going to break it down into primes. This one will divide by 2, won't it? And that'll divide by 2 again. And that'll divide by 2 again. 2's are easy for me. Look, I see a perfect cube. 2 times 2 times 2. So if I knew that 8 was a perfect cube, if I remembered that, if I had memorized that, I could have just written this as 8 times 3, okay? And then I would have taken the cube root of 8. But let's do it like this for this one more time, and then I'll start trying to shortcut it for you. This is the cube root of 2 times 2 times 2 times 3 times x squared, because I can't get a cube root. I can't get a cube out of x squared, can I? Here's my perfect cube, 3 of those 2's. When I take the cube root of them, I get a 2. And I have to multiply that 2 times whatever's out front, don't I? A negative 5 is out front. 2 times negative 5 gives me negative 10 times the cube root of whatever was left over in here. These are the things I was not able to simplify, a 3 and an x squared. Now, look at my 2 terms there. I have 2 terms, but are they like terms? Do they have the same radical? You should be saying yes. That is the same as this, isn't it? So pretend they're just a variable like an x. 3 minus 10. What do you get when you say 3 minus 10? So I have negative 7, whatever the radical was, right? I told you this is going to be a little complicated. It's about to get a lot complicated. So if you are not certain of radicals, you're going to have to pay really close attention today. And you're going to have to watch this tape several times, and you're going to have to do your homework multiple times, okay? Because radicals are hard, okay? All right, let's go on to the next one. The next one is negative 6 cube root of 2 minus 12 times the cube root of 2. I'm sorry, the square root of 2 plus 5 times the square root of 2. Now look, under these radicals, there's nothing to be done, is there? I can't get the square root of 2. I can't get the cube root of 2. So I can just look and see if I can combine like terms. Listen to me carefully. The cube root of something is not the same, the cube root of 2 is not the same as the square root of 2. These two are not alike, are they? But these two are. So what I do with the first one, which doesn't match anything, is just bring it down. What I do with these two is just say, okay, that's the variable, that's the radical. I treat it like a variable. I can do the math with the coefficients. Negative 12 plus 5 gives me, somebody make it so that I'm not the negative 7. Thank you. Just don't want to be the only one doing math in the room, guys. Okay, next problem. 9 times the square root of 2 plus 4 times the square root of 2 plus 10 times the cube root of 2. You should be able to do that one from the last example. I'll do it real fast. Done? Yes? Easy? Good. Because these match, don't they? That one doesn't. So I'm going to do the math with these two, and I'm going to say 9 plus 4, 13 square roots of 2, plus nothing I can do about this one, is there? It's a cube root, not a square root. Do you understand? The radicals, if you're going to combine them with addition and subtraction, listen, this is the rule for addition and subtraction. They have to match exactly, okay? So let's get it a little more complicated down here with this one. What I have is 6y. Notice the variable is part of my, I want to call it coefficient out here, isn't it? I've got 6y times the square root of 50y plus 3 times the square root of 8y cubed. Now, I can see all kinds of square roots in there, and maybe you can too. So let's start with what we see. Let's say we want to break 50 down. Do you see a perfect square that is a factor of 50? 25. 50 is the same as 25 times 2. 25 is a perfect square. Now you could break it all the way down. If you wanted to go to primes, you'd end up saying 5 times 5 times 2, wouldn't you? Or you can say, I see the perfect square. I'm going to rewrite this as 6y times that perfect square 25 times 2 times y, and I know that I can take the square root of 25. That brings it out from under the radical as a 5. There's your shortcut. Okay? That's to keep you from having to always go to primes. When you start seeing perfect squares or perfect cubes, you can just factor them out, take the square root or the cube root, whatever root you got, and then whatever's left still stays. So let's go ahead and simplify this. I have to multiply it times what's out front, don't I? Well, 6y times 5 gives me what? Exactly. And what's left under the radical? Okay, that one's done. Let's go to this one. I want the I want the square root of 8y cubed. Well, do you see a perfect square inside 8? Yes. What is it? 4. You got it, guys? Are you following? There's 4 times 2, right? I could break it on down to primes. It would be 2 times 2 times 2, and I would take 2 of those 2's and get the square. But this is my shortcut. So I'm going to write it again. What's the square? 4 times 2 times, okay, let's go ahead and break this one down. There's the square, y squared, times y. We did this before, so it should be familiar, right? What can I take the roots of? Well, 4, the square root of 4 is 2. The square root of y squared is y. What's left under the radical is 2y, right? You understand what I brought out gets multiplied, and it has to also be multiplied times that coefficient. So I've really got 3 times 2 times y. That was a positive, separating them. 3 times 2 times y is going to give me 6y. What's left under the radical then, I've circled it so I don't lose it, because this gets really confusing after a while, is 2y. Make sure you understand this one before we step into the next problem, okay? Are you getting it? You're not just copying it down, right? Yes?
How come the y on the outside was taken from
This one right here,
Oh, on the right side.
right here. This,
6y right there. How does the y get there?
oh, it was there in the problem.
Oh, okay.
That was the original problem. We started with 6y outside the radical. Was that your question? Did that answer you? Anything else that's not clear? It's said, you got it? Okay. I mean, it's going to get really confusing, guys. This is about to get a lot harder on you. If you thought the first test was hard, you probably need to come see me. Okay? Because math is going to get tougher as we go. You either got a lot of time you're going to have to spend in it. If you're struggling, you're going to have to devote some time here. Okay? All right, let's do another. Oh, wait, I haven't finished, have I? Okay, so I've got, now look, do I have like terms that I can combine? Now, this one's tricky because, look, I have the radicals are the same, but there's this variable outside. So here's the deal. Are you listening? Everything after the coefficient must match. The coefficient is the number. Everything else has to match exactly if you're going to add and subtract. In other words, I have 30y times the square root of 2y's, and I have 6y times the square root of 2y's. Those match. Therefore, I can just add those terms and end up with 36y times the square root of 2y's. Okay? Be careful. Everything has to match, or you cannot add and subtract them. You can multiply, you can divide, but you can't add and subtract. Okay? Some of you are looking at me like you're scared now. It's going to be okay, but you are going to have to put some time into this, okay? Let's go on to the next. All right, now I've got weird problems here. I've got fractions. Really love fractions, don't you? I told you there's two ways to work them. You can take the fraction, if it works, I mean, you can take it and split it into a radical in the numerator and a radical in the denominator, or inside this single radical, you could simplify it if you can, but we can't. 147 does not divide by x to the fourth, does it? I mean, it's as simple as it gets. So we'll try our second method. We'll try 147, the square root of 147, over the square root of x to the fourth. I'm good with x to the fourth, aren't you? Isn't that a perfect square? Can't I go ahead and say, okay, I know what to do with this one. I'll bring it out from under the radical as x squared. Just write it down. But I don't know what in the world I'm going to do with 147 because I really don't see any perfect squares in it because I'm not really familiar with 147. So I'm going to have to take it and try some stuff. It won't divide by 2. It won't divide by 5. Those are my easy tries. So I look at 3. Well, 1 plus 4 is 5, plus 7 is 12. Well, that divides by 3. So I take my calculator and I go, okay, 147 will divide by 3. 147 divided by 3. I got 49. Now, do you see a perfect square? What is it? 7 times 7 is 49. So at that point, I don't have to do anything else. I mean, I could break it on down, but I'd be saying 7 times 7, right? So I'm going to just rewrite this one. Running out of space here. I'll rewrite it down here. I'm going to say this is really the square root of 49 times 3. And I already simplified this one. It's over x squared, isn't it? Okay, let's finish this term because it's hard to leave it and come back to it. 49, square root of that, comes out of the radical as a 7. So what I have when I finish down here is 7 times the square root of 3 over x squared. Okay, finished with that term. Let's keep going down this other side and see what we have. I'm going to say this is the square root of 3 over the square root of 4x to the fourth. This is good because both of those are perfect squares, aren't they? Square root of 4 is a 2. Square root of x to the fourth is x squared. So I took everything out from under the radical. There's nothing I can do with that numerator. Let's just write it down. It's the square root of 3, isn't it? And down here I've got 2x squared. Okay, well, I've got to keep on writing because I've not lined it up with my final product over here. There I go. Just keep bringing it down until you have the two terms together, and then you got to decide what you can do with those two terms, right? At this point, I don't have a common denominator, do I? But I can get it there, can't I? Okay, so I've got x squared, 2x squared. What would my least common denominator be? Do you understand that? The least common denominator has to include something that 2x squared can be divided by. Well, if I just have a 2x squared over here, and all I have to do to get there is multiply this side times 2 over 2. Remember, I can multiply a fraction times anything over itself, and I'm only multiplying it by the number 1, right? So this is good. I can say 2 times 7 is 14, cube root of 3. And this would be 2x squared down here. And I don't have to change this one at all, do I? Okay, I know you're running out of paper. This one I probably should have given you more space on some of these problems. So if you have blank paper, you might want to, as we go forward in this section, you might want to start writing them on blank paper so you have more room. I'll try not to let it get too confusing here. Look, I have a common denominator. I'm going to come right over here and I'm going to write everything over the common denominator. So that would be 14 square root of 3 plus 1 the square root of 3. Isn't that 1 times the square root of 3 there? What's 14 plus 1? This is 15 square roots of 3, right? Over 2x squared. Now at this point, all you could possibly do would be to simplify that 15 and 2. If they reduced, you would reduce them. If it was 14 and 2, you would end up with 7, but it's not. It's 15 and 2, so you're pretty much stuck. But learn to check for that anyway, okay? Okay, are you okay? You're going to replay the tape is what you're going to do. And listen to this video again and again until you get this, all right? All right, let's go on. Why did the 14... Okay, do you see it? Okay. All right, let's go. Next page. I've got 20 square root of 27 minus the square root of 147. Now, you should be able to break that down pretty easy. Do what we did. Find the perfect squares in 27 and 147. And go for a hint. Go back to the first page. Didn't we already do 147 already? We factored it. You can see the perfect square from work you've already done. See if you can do that example or first example there. While you're doing that, some of you are working, if you're working ahead, let me help you. If this is easy for you, this problem is written wrong. It is not a radical inside a radical, okay? So do that with that second problem. Oh, got it. And you can also get rid of example number 7 because we already did that one on that page, okay? All right, I'm going to start it. Look up here if you need help. I'm looking for perfect squares inside 27. And I found one. And I'm looking for perfect squares inside 147. And I found it. That's what you have to combine, okay? So you should have come up with 3 minus 7, which would give you a negative 4 square roots of 3. Okay? You good? Okay with that one? Okay, that was one of our simpler ones. Let's keep going. I've got this one. I can see a perfect square in x cubed, but I can't see it in the 2. I can see a perfect square inside 18. So I'm going to just rewrite this real quick, since it's so confusing anyway because I typed it wrong, as 7 times 2 times x squared times x. That way I know that I'm going to take out the x squared, the square root of it is x. Okay, kind of gotten that taken care of. Plus 4x, and I see the perfect square inside 18. 18 is 9 times 2, isn't it? If you get in the habit of writing the squares, perfect squares first, it makes it easier. Square root of 9 is 3. Now all I have to do is take the parts that I have removed from the radicals, multiply them by whatever's in front, and simplify, okay? This was what's left in there, and this is what's left in here, right? Whoops, sorry, missed a 2. So I've got 7x times whatever was left inside that radical. Looks like 2x. And this is going to be plus a 4 times 3, which is 12x, times whatever is left in the radical, which looks like a 2x. Okay, now look what I have. You can't just look at what's the radical because there's a variable outside. Okay? So we have to say everything has to match. Everything after the number coefficient has to match. Underline it and check it. Does it? Okay, so we can add them. We say 7 plus 12 is 19, and we say, what are they? X to the, times the square root of 2x's. How was that one? Did you do that one okay? Okay, let's do number 3 then. You've got 3. You're looking for the square roots. You should be able to simplify fairly quickly. Find the square roots inside 75, 50, and 48. Bring them out from under the radical. This one is not hard. It's just a little longer because it has three terms instead of 2. All right. If you're not used to this, I mean, it takes practice, right? But most of us can see the perfect square in 75 and in 50 because we're used to dealing with quarters, aren't you? And a quarter, 25 cents, 50 cents, 75 cents, that helps a little bit when you're trying to do this. So I see the perfect square. It's 25 times 3 gives me 75, and I can take the square root of 25, and it's always 5. I do the same thing over here. 50 is 25 times 2. Perfect square is 25. When I bring it out from under the radical, I take the square root, it's 5. But 48's not so easy, is it? So now you could take it and break it down by 2's, but maybe you saw a shorter cut. Maybe you saw that it was divisible by 4, and you know 4 is a perfect square, right? So that's the shortcut I took. I said 4 times 12 gives me 48. Well, okay, I see another perfect square inside 4. I see 4 times 3. Well, I got 2 perfect squares. I'll just write them down and then take the square root of each of them. Do you see there's another perfect square inside 48 that I didn't use? Anybody want to tell me what it is? It would be 16. But we're not used to that. It's quite all right to go this way, you know. It's quite all right to break it all down to primes. You may have a problem with time if you're breaking everything down to primes every time, okay? But still, I broke it down pretty far, and I said square root of each of those is 2. That doesn't take me too long. I'll just multiply them together and say 4, won't I? So let's simplify, finish this one. I have to multiply that times the 3 that's out front, so I have 15. What's left under the radical is just a 3. Here I'm going to multiply again. I have another 15. What's under the radical is just a 2. And here, I'm going to multiply these 2 that I pulled out, 2 times 2, and multiply them times 1, right? That's my coefficient here. 4 times the square root of 3. Now, which of these terms can I combine? Can I combine the first one and the second one? Can I combine the first one and the third one? Yeah, so that's all I do. I say, well, this one is like this one. Right? They're both positive, so I'll just add them together. 19 times the square root of 3. And don't forget, you had that 15 times the square root of 2 still there. Those are not like terms, so I cannot add and subtract them. Okay, next, cube roots. I'm not expecting you to be really familiar with cubes at this point, so what I would suggest is that you break them down. Start with primes. Go to primes. If you don't see perfect cubes, inside 81 and 192, and there's no perfect cube inside those x variables, so that you're stuck with that under the radical, aren't you? But let's see what we can do about simplifying the 81 and the 192. And I would suggest that you start by dividing each of them, or that one, by 3, and this one by 2, right? Take them down and see if you find perfect cubes. You're going to write it out, write the primes out, and then look for 3 numbers that are the same, okay? Okay, I'm rushing you a bit, but we're going to run out of room time if I don't. So look, I factored 81. It happened to factor into 3 times 3 times 3 times 3. I just need 3 of them to make a perfect cube. So I'm going to take these first 3. I'm going to say that bringing them out from under the radical, they would be 3, right? What's left under there? The 3x. Before I forget what I've done, let me go ahead and write this down. I've got 3 times the cube root. There's too many 3's in this problem. Cube root of 3x, right? Be careful when you're writing the index that it doesn't look like part of that coefficient, okay? This is the index. It has to be little and up next to the radical sign. It's subtraction, so I don't forget my subtraction sign, but look what I've got. I've got 3 2's. Cube root of those is 2. I've got 3 more. I'll do it again. Cube root of that is 2. I don't have to multiply those together, but what's left under the radical is 3x. 2 times 2 is 4, times the coefficient of -1 is -4, isn't it? Times the cube root of whatever was left, which is 3x. Now it looks simple. You know what to do, right? This matches everything after the numerical coefficient matches. So I can just say 3 minus 4. That gives me a -1 times the cube root of 3x. Okay? Okay, let's look at this next one real quick. I've got a to the 5th times the square root of 4ab cubed. Well, let's just take this one step at a time. I know 4 is a perfect square, don't I? And I see the perfect square in b cubed, so I'm going to rewrite it. A to the 5th is the coefficient. I'm going to write my perfect squares so that I can pull them out. A cannot go anywhere, but b cubed can become b squared times b, can't it? This one has a perfect square, a square root, and this one stays. Before I forget what I've done, I'm going to go ahead down and simplify that further. This is a to the 5th times 2 times b. Write your variables alphabetically, okay? Numbers come first. 2, a to the 5th, b, okay? It's easier to see if they match if they're written in the same order. Next, I'm going to say minus, and this one is a perfect square, isn't it? 25 is a perfect square. It can come out as a 5. A to the 11th, what if I split it into the biggest even number times a and take that out as a perfect square? I say 10 divided by 2, don't I? And I get a to the power of 5 times a. B cubed, well, that's going to be b squared times b, isn't it? This is a perfect square, and this one has to stay. All right, so finish that one. Don't forget the minus in front. All of this is out front now. 5, a to the 5th, b. Left under the radical, it's easy to see because I circled them. What is it? Well, it's ab. Did I forget to write the radical in the last one? I did. Sorry, guys. What was left under that radical was ab, wasn't it? Okay, let's go on to the third term. This is plus. Do I see a perfect square inside 81? Well, 81 is a perfect square, isn't it? If I take that one, I'll pull out the perfect square of 9. And I'm going to do the same thing here. I'm going to make this the largest perfect square I can find, whatever's left over. Largest perfect square I can find times whatever's left over. And I'm not writing the little dots between them. You know that that means they're multiplied when they're right next to each other. This one comes out as a to the 5th. This one has to stay. This one comes out as b. This one has to stay. So now I've got 9 plus, right? 9 a to the 5th b times what's left under the radical. Well, this is why I told you to circle it. It gets really confusing as these things get bigger, doesn't it? Now, look carefully. Do these terms match? You see it? Not just the radical. We have to look at everything after the numerical coefficient. This one is just a 2. So I'm going to draw a line. That has to match everything after this 5, which has to match everything after this 9. What are they? Well, they're a to the 5th times b times the square root of ab's. Since they all match, we can pretend they're x's. is just x, okay? And I can say 2 minus 5 plus 9, right? Well, 2 minus 5 is negative 3. Plus 9, negative 3 plus 9 would be like 9 minus 3, wouldn't it? Or I got 6 of these, don't I? Did I do that right? Yeah, I think so. It's not the same answer I got when I was doing it before. But I think I did it wrong before. I did. Okay, good. 6. I was working really quick last night. What have I got? 6. Everything that's after the numerical coefficient. Okay? All right, last one on this page. Let's go with 6y times the square root of 50y plus 3 times the square root of 8y cubed. This one should be an easy one for you. Do this one really fast. I can't give you but a half a minute, but you should be working real fast on these. Okay, solution is there. Any questions? Some of you look like you've been hit with a ton of bricks. This is hard, isn't it? Confusing? Complicated? You just have to get the rules down. Do the same thing every time. Look for the same things every time. Get familiar with your square roots and some of your cubes. Some of your cubes will help you, okay? Do you need an explanation or are you good? It's the same thing I've been saying over and over, isn't it? Square root of 25 times 2. I broke down 50 because I saw the perfect square 25. Square root is 5. I multiplied that times my 6y. I got 30y. What was left under the radical was just 2y. Over here I see that 8 is a 4 times 2. 4 is a perfect square. So I bring out my 2. Y squared times y gives me y cubed. So I bring out the square root of y squared, which is y. So I say 3 times 2 is 6 times y. That gave me 6y times the square root of 2y. And look, everything matches after the numbers. So I've got y times the square root of 2y's. I've got 30 of them over here, 6 of them over here. Add them together, and I have 36 of them. Are you good? I know that 7th problem we've already worked, so you can skip that one. Okay, we're moving into something a little more complicated. Okay, so let's say that now we want to be able to multiply. So 2, it's a square root. So we have to have the same index. As long as we have the same index, and whatever is under the radical sign can be multiplied together. Got it? As long as we're dealing with like radicals. So I'm going to distribute this multiplication. I'm going to say the square root of 11 times the square root of 11 is really the square root of 121. But here's a thing that you need to start looking for. That's a perfect square, right? I could write it as the square root of 121, but I could also recognize that I'm multiplying a radical by itself. Anything times itself, the root is one of them, okay? If I were to say 2 times, or let's see, okay, do it this way. The square root of 4, right, times the square root of 4, well, what's the answer to that? It's just 4, isn't it? Do you understand that? Okay, so how do I mean, what I'm saying is if I square a square root, I have whatever was under the radical. In other words, if I multiply it times itself, I have whatever was under the radical. I can simplify in that one step. All right, so I could say the square root of 121, but then I recognize square root of 121 is 11. So this is just 11. You can do that really quickly if you're multiplying a radical times itself. Take whatever's under the radical, get rid of the radical sign, okay? But this one is not so good, is it? This time I'm saying the square root of 11 times, okay, well, it's got to be times plus y. That has to be multiplied out there, doesn't it? And then I've got, look at this, 11 times 55. But now listen, we know that we're going to have to factor it, right? After we do this, we're going to have to factor to see if we can find perfect squares. So let's don't multiply it. Let's say 11 times 55. And then let's go ahead and break down 55 into 11 times 5, because you guys know that one, right? So what is this in essence? Well, it's really y times the square root of 11 times 11 times 5. That kept me from having to factor it again. It was already basically factored. So now I can say, well, this is a perfect square, isn't it? It comes out as an 11. I had 11 over here, a whole number, plus I'm going to say now I have 11y. What was left under the radical? Only a 5. There's your way to think about these, okay? I know it takes some twisting your mind around it. Let's try the next one. I'm going to say square root of 7 times square root of 2. Well, those are not the same radical, are they? So all I can do is multiply them. 7 times 2, there's no perfect squares in there. So I'm just going to multiply it out and say 14. And then I'm going to do the next one. I'm going to say square root of 7 times the square root of 6. Well, that gave me the square root of, I don't know if there's perfect squares inside it or not, but I know it's 42. So now I'm going to check it. I'm going to say, well, can I simplify 42? I already know I can't simplify 14. There's no perfect squares in it. This one would be 2 times what? 20. Why can't I do that? Why can't I not do that? 21, right? 3 times 7. You see it? There's no perfect squares in it. I'm stuck. That's what I've got. Square root of 14 plus the square root of 42. But that's how you check it. Take it to primes and see if there are any squares. All right, let's look at this next one. This is, and you should recognize it from your last test, this is a FOIL problem, isn't it? So I'm going to rewrite it. I'm going to say it's the square root of 5 minus the square root of 3 times the square root of 5 minus the square root of 3. And I multiply the first terms. Well, they're identical. Square root of 5 times the square root of 5 is what? What's the answer to that? Yeah, we don't have to say square root of 25. We can just say 5, can't we? Let's multiply outside terms. Square root of 5 times the negative times the square root of 3 is going to give me, well, those are not the same. Inside terms, got the same problem. They're not the same. And last terms, look, negative times negative is a, so let's settle that. Square root of 3 times square root of 3, what are you going to get?
3.
Just a 3. Don't say square root of 9. I mean, you can say square root of 9, and then you go, oh, that's a 3, isn't it? Now, what do I have that is alike that can be combined? Well, this 5 and this 3 can be combined. They give me 8. And this is a negative 1, isn't it, times the square root of 15, and that's a negative 1 times the square root of 15. So how many square roots of 15 do I have? Negative 2, right? Don't forget, this is a -1. This is a -1. -1 minus 1, -2, right? That's as simple as that one gets. Is this easier than adding and subtracting them? Yes? No? Okay, next. FOIL again. The terms are a little more complicated, but the first terms, I'll draw the line. First terms are pretty easy. Square root of 5x times the square root of 5x. What do you have?
5x.
Yep. Okay. Outside terms. Square root of 5x times a -2 times the square root of 7x. Well, those are not the same terms, so I'm going to do the multiplication. -2, right? Because I multiplied this 1 that's out in front times that -2 times the square root of what? I have to multiply what's under the radical. I have to say 5 times 7 is 35. And x times x is x squared, and some of you consistently did that wrong on the last test. You cannot go further in this class until you understand x times x is x squared, okay? All right. Next, let's look at the inside terms. Negative times positive is going to give me a negative. I'm going to say 4 times 1 is 4. And what have I got here? Same thing. 7 times 5, x times x. And then last terms. Well, I'm saying -4 times -2, +8. Square root of 7x times the square root of 7x. What is that? So I'm just going to say times 7x. I already wrote down the 8. It gives me a chance to fix it later. All right, so what do I have that's alike? Well, can we just say this one is really 8 times 7x, which is 56x, right? I'll just rewrite that. I have a 5x, and I have a positive 56x. When I combine those, I get 61x. And these match, don't they? So I've got a -2 minus 4, -6, times the square root of 35, x squared. Okay, at this point, I'm not done because there are some perfect squares under that radical, aren't there? Now, 35 doesn't have any. If I factored 35 to primes, I would say 5 times 7. There's nothing perfect square about 35, but x squared can be brought out, and it becomes an x, doesn't it? Okay, so let's rewrite it. 61x. Anybody? No, because everything after the number does not match. These are x's. These are x times the square root of 35's. Okay? All right, another problem. See which one of these I want to work, because I'm probably not going to work both of them. Okay? So for this one, I'm going to say FOIL it, okay? Actually, you try it. Give it a chance. First terms, outside. See if you can combine, simplify, get it down to where you have unlike radicals. Okay, I've finished the first step. Now, if you've done the FOIL and you want to check where you are, there's no sense going any further if you mess that up, right? Check and see. See if I got it right. Then you start simplifying under the radicals, okay? If you see perfect squares, you're going to bring them out. Okay, that was written kind of, I sloped as I went down there writing it, but let me just rewrite the answer for you so you can look at it. The first term is 4x. The second one is negative 6x times the square root of 6. The third one is a negative 12x times the square root of 3. And the fourth one is a positive 5x times the square root of 2. And nowhere in there do I see anything that can be combined. They're all unlike terms. You understand where this came from? I took 12 and I broke it down into 4 times 3 because 4 is a perfect square. Only thing left under the radicals is 3 because I took the square root of x squared. And down here I said 18 is 9 times 2. Square root of 9 is 3. The 2 is left, but I take the square root of x squared and it's x. Multiplying all these together, I'm saying 18 times 3 gives me my, 54, right? It's 54? 54, sorry guys. 54, and then I multiply that times x. So, and it's left under the radical is a 2. It's not hard, it's just complicated. Now this next page is hard, okay? So if you've been struggling, or don't fall asleep on me, okay, this one is really confusing. If you're confused now, you'll be more confused in a minute. So like I said, go through this a lot of times before I see you again on, what is today, Wednesday? Before I see you again on Monday, there needs to be a lot of work in this section, okay? So here's what we've got. We've got, what if we have an index, what if we have an exponent that is a fraction? Actually, that is there's a way to transfer between fractional exponents and radical notation. Here's the thing I would keep in mind right here. If I had a term and it was raised to the power of a fraction, then what I'm really saying is that bottom denominator is the index of my radical, and that top, the numerator, is the exponent of the whole thing, which can be parentheses and the exponent on the outside, but that also is the same as this exponent under the radical sign, okay? So we sometimes go straight from here to here. And the way I kind of remember that is I say, okay, this one is going to go to the left and up. This one is going to go to the right and down. You know, that's where I'm going to put those fractional exponents. So if you had this one, in other words, if I had, what is this? This is the square root of x to the power of 1, isn't it? Okay, so write it as a fractional exponent. Well, this one came from the denominator, didn't it? This one came from the numerator of the fraction. Keep this page with you because you're going to want to refer back to it as you're trying to translate these fractional exponents into radicals and radicals into fractional exponents. You're going to go back and forth with this thing. So now let's take this one, and I'm going to say it's a negative 8, and that negative 8 is being raised to the power of 2/3. Well, here is my index, isn't it? Here's my index right there. It's going to be, if I write it as a radical, it's going to be the cube root of something. Cube root of what? Cube root of negative 8. And I would probably come out here at that point and say all of it raised to the power of 2. Is that okay? You could also say this. You could say the cube root, that is really the cube root of negative 8 raised to the power of 2. Those are the same thing, okay? Those are the same thing. Now, negative 8 times negative 8 is what? Okay? And if I could take 64, can I get the cube root of 64? Anybody know their cubes that far? 4. So what have I got here? Since that's a negative times a negative, I'm okay with this. It becomes a positive 64. The cube root of 64 is simply 4. If you didn't know that, you would break it down to primes and find it. But like I said, it's good to know the cubes up until at least 6 cubed, okay? All right, so let's do another. This time I don't want this one to be negative. Change that. Positive, okay? So let's just make that a positive because this is confusing enough as it is. And let's say the root that we're looking at is the 4th root, isn't it? The 4th root of what? Of 256. And I could say all of that raised to the power of 3, couldn't I? Okay, so I might do it that time because this is a really big number. 256 is huge. And so I might just say maybe I can find the 4th root of 256 before I cube it, right? Because I don't want to have to factor any bigger number than 256. And so I take 256 and I break it down. And it's 2, so I can say 2 times, okay, I'm going to help you with this one because we're in a hurry. And if I break it down again, it's 2 times, what was that, 64. And 64 is 2 times, 32. And this is 2 times, what is it, 16? And this is 2 times 8. And this is 2 times 4, right? So if I want the cube root, if I want the 4th root, right, I have to have 4 numbers multiplied together that would give me that. Well, how many do I have? 1, 2, 3, 4. Okay, didn't keep going, sorry. I have 1, 2, 3, 4. There's one set of 2's. And I have 1, 2, 3, 4. I actually have 2 sets of 2's. I'm going to be able to say those are my 4th roots. If you wanted to write it down, I would come somewhere else on this piece of paper and say the 4th root of 256 is 8 2's written together. And when I'm taking 4th roots, I'm taking them 4 at a time, so that's 2. And here's another set. That's 2, right? So what's the 4th root of it? 2 times 2 are 4. Whew, I finally simplified. The 4th root of 256 is really 4. So what do I have? 4 cubed, right? It's easier sometimes to see if you can simplify the radical before you go raise it to an exponent. If your numbers are really big, what was your other option there? 256 cubed, and then try to take the 4th root of it. This is simpler to me. Break down the smaller number, see if you can get the 4th root, okay? I know that doesn't ring a bell, but you got me on video. You can listen to that again, okay? All right, let's see if we can change this one. Now, it looks ugly because it is a fraction, is what it does. But what you really have to do is start thinking of it as, okay, I'm just going to put it under the radical sign, right? I'm going to put that radical, I'm going to put 4 over 81 under a radical, and then I'm going to raise it to the power of 3. Why did I not write an index here? Because it's a 2. You can write it if you want to, but it's a square root, isn't it? Okay, so now I've got square root of 4 over the square root of 81. Let's see if we can simplify that before we go raising it to the power 3. I would break these down into 2 radicals because they're both perfect squares, aren't they? I know I'm going to have to raise it to the power of 3 in a minute, but let's go over here and say square root of 4. Well, that's just 2. Square root of 81, that's 9. All of this raised to the power of 3, right? Can I simplify my fraction here? So I just multiply. 2 times 2, 9 times 9. And let's see, does that simplify at all? Oh, sorry, 2 times 2 times 2, cubed. 2 times 2 times 2 is 8. 9 times 9 times 9, which is 729. Just thinking squares. Sorry. Then that doesn't simplify. I know, because I just came from 9 times 9 times 9, didn't I? All right, and I could have broken it all down to 3s, and nothing's going to simplify with 8. All right, I may have to finish this when we get back, because this next one, I mean, they do get more confusing. I would prefer that you go in there to my lab math into 7.2 and try some of these problems, okay? Do this for me. Do the help me solve it, right? Walk through the steps, and then come back, and I will try to tack this onto the beginning of my explanation on Monday, okay? But just try it.